Hello, we're back again, and where we left off last time, we were going over naming of ionic compounds. And the last thing we did was naming ionic compounds. This is section 3.5, naming ionic compounds that contain um, polyatomic ions. And one last thing under naming of ionic compounds that we need to mention is hydrated ionic compounds. Ionic compounds, generally involve metals and nonmetals or polyatomic ions. But it's one unusual aspect of some ionic compounds is that in order to stabilize the ion, they tend to attract a certain number of water molecules. And those water molecules are only physically attracted to the ionic compound. They're not chemically bonded to it. But they are physically associated strongly enough that there tend to be a consistent number of water molecules for each formula unit of the ionic compound. And so the H2Os are generally included with the formula for the ionic compound, although we have to have some way of distinguishing them from the parts of the molecule that are chemically bonded to each other. Okay, so the waters are physically associated with the ionic compound, but not bonded to the ions. And these are known as waters of hydration. And in the formula, they are separated from the rest of the formula by a dot at the end. Okay, so they come at the end. And probably the easiest way to convey that is to show one. Copper sulfate pentahydrate, and we'll get to the naming in a moment, is basically an ionic compound. It's a pretty blue powder, kind of a royal blue color, and it has the formula CuSO4, that's the copper sulfate, but each unit of CuSO4 has 5 water molecules associated with it. And so we write CuSO4 dot 5H2O. And the dot represents that the H2Os are part of the molecule, or they're part of the formula because they're there, but they are not chemically bonded to the rest of the molecule. It's a physical, attraction. And the waters of hydration in most cases are removable by heating. So if you take some copper sulfate pentahydrate and you heat it, and the triangle over an arrow means heat, what you get is what's known as anhydrous copper sulfate plus 5 H2Os. Technically, we should be calling this copper 2 sulfate because copper is a transition metal. So an ionic compound that normally has waters of hydration, if you drive those waters of hydration away by heating it up, you would then call it anhydrous, and then the name of the compound. Anhydrous just means without water. Hydro is, from the Greek word for water, and an, as we saw with anion, a or an in Greek is a prefix that negates something. It means, not or without. So anhydrous literally means without water. So this would be hydrated, this would be anhydrous. Okay, let's see. One thing we haven't mentioned yet about the hydrates is naming. So let's see. So naming hydrates or hydrated ionic compounds, if you prefer to call them that, the name takes the form of the name of the compound, then the prefix telling how many water molecules there are associated with each formula unit of the compound. And then the word hydrate. The prefixes, as I mentioned, just give the number of H2Os associated with each formula unit of the compound. Okay, so here are the prefixes. And the number that they represent. First of all, hemi means half. And you might wonder, how can a formula unit have half a water molecule associated with it? You know, either you have a water molecule or you don't. If you cut it in half, it's not water anymore. But the answer is that this just means that that water molecule would be shared by 2 formula units of the compound. So each of them gets half when we boil it down to like 1 formula unit. And then we go for their whole numbers. Mono means 1. These prefixes are derived from Greek, so we use mono for 1 instead of uni, like with the covalently bonded compounds. Which we haven't actually gotten to yet, so that's a bit of a preview. 2 would be di, and 3 would be tri, and 4, not quattro, that's Latin, this is penta. Oh, sorry. Tetra for 4. And then penta for 5. You may recognize these terms, of course, from geometry. Pentagon has 5 sides, and that's because a lot of our geometric terms are taken from Greek. 6 would be hexa, and 7 would be hepta, and 8 would be octa, and 9 would be nona. And there are some examples here and there of compounds that have, say, 2.5 H2Os associated with the formula. And that just means that basically there are 5 H2Os that are being shared kind of equally by 2 formula units. So we assign 2.5 to each of them. But those are rare enough that we don't really have to worry too much about them. And so we'll just go with these prefixes. Okay, so some examples. The one that I mentioned before, CuSO4.5H2O, this is copper 2 sulfate pentahydrate. That's a favorite one for using in the lab because it's a pretty deep sort of royal blue color when it has the waters of hydration attached. But then you put it in an oven or over a Bunsen burner and heat it up for a few minutes, and the anhydrous version of it is white. but you can get it to turn back to that same shade of blue just by adding a little water to it. Let's see, there's also CuCl2.H2O, and that's copper 2 chloride. Monohydrate. And normally you would write the names all on one line, but I'm running out of space here. There's Epsom salts, which is magnesium sulfate heptahydrate. Now you know why they call it Epsom salt. And let's see, CaSO4.12H2O. So this is an example of an H2O molecule being shared by 2 formula units of the compound. And that's calcium sulfate hemihydrate. Okay, so it's just naming the ionic compound, and then you use the prefix to say how many H2Os there are, and then you follow that with the word hydrate. So not too difficult. Okay, so section 3.6 is about naming molecular compounds. Okay, the rules for this are different from the rules for ionic compounds. So it's important to be able to spot or to be able to identify what type of compound it is. So it's important to be able to tell the difference between an ionic compound versus a molecular compound. So once again, remember ionic compounds would be a combination of metal and non-metal. Or polyatomic ions. So there are a couple of, say, any ionic compound that involves the ammonium ion, for instance, would not have any metals in it. But, you know, basically, it's going to involve a metal or the ammonium ion and one or more nonmetals. And molecular or covalently bonded will be made up entirely of nonmetals. So again, so that means in turn, it's important to be able to distinguish which elements are metals and which ones are nonmetals. Okay, and you can always look at the periodic table because they are arranged so that they occupy separate areas of the table, but you do need to know which areas those are. Part of the problem with naming molecular compounds is that nonmetals can often combine with each other in multiple ratios. Okay, and what we mean is carbon and oxygen can form CO2 or CO. Hydrogen and oxygen can form H2O2 or H2O. And even then, it might not be too bad if there are only 2 possibilities for any given combination of nonmetals. But in many cases, there are many different combinations possible. And there are others too, but I'll stop there. So nitrogen and oxygen, for example, can form NO, NO2, N2O, N2O3, or N2O5. And there are a couple others too, but I think that's enough to illustrate the point. Okay, so it's difficult to predict the formula from the elements involved, and we have to have a way of distinguishing one compound from another, even though it involves the same two elements. So for naming, well, many of them have, some of them have common names. That are still used even in chemistry, like water and ammonia. But actually, even those compounds have formal names. They can be named according to the rules that we're going to see also. But there are actually too many to rely on common names for all of the known molecular compounds. There are literally tens of millions of molecular compounds known. You know, chemists, when they first started really seriously investigating things back with the alchemists in the Middle Ages, they often did give common names to all of these compounds. But after a while, it became really, really difficult to keep track of all of them. And so, you know, more recently, we've had gone through sort of several ways of trying to assign formal names to all of these compounds. Some of the ways of doing it in the past have turned out not to work so well, as even more compounds have been discovered as time goes on. And so every once in a while they change the systems for the formal names. But the one that we have, the formal system that we have now, works pretty well. Naming binary molecular compounds. That's the ones with two elements in them. Is pretty simple, actually. First of all, you name the more metallic element first. And remember, you might be thinking, actually, what are you talking about? The more metallic element first. You just said that molecular compounds consist entirely of nonmetals. But remember what I said previously, being metallic is not an all or nothing sort of thing. Metallic qualities are things that can be kind of measured in degrees. Because being, and it's sort of like the degree to which you want to do the things that metals do, versus not wanting to do the things that nonmetals do. So a metal basically loses electrons to become a cation. A nonmetal gains electrons to become an anion. And so, and there's a different degrees to which elements want to do those things. So basically, the more you want to gain electrons to become an anion, the less metallic you are. And the more, or the less you want to gain electrons to become an anion, the less non-metallic or the more metallic you are. In practice, since the metals occupy the left-hand side and center of the periodic table, and over on the right-hand side, even some of the elements down toward the bottom are metals, metallic quality is considered to increase as you go towards the left in the periodic table and as you go towards the bottom. So if you look down in the lower left-hand corner of the periodic table, you see elements like cesium and francium, and those are considered to be the most metallic elements of all. And if you look at the upper right-hand corner of the periodic table, excluding the noble gases because they're unusual in that they don't want to gain or lose electrons. But if you look at the upper right-hand corner of everything except the noble gases, you see fluorine, which is the least metallic element of all. And that's because fluorine has a voracious appetite for more electrons. It does absolutely not want to give up any electrons, which makes it very non-metallic. Cesium and francium down in the lower left-hand corner will practically throw electrons at you just for looking at it, just for looking at them. So they are considered to be very metallic elements. And all of the other elements are somewhere in between. So the general trend is that the more metallic element is whichever one is to the left or below relative to the other element in the compound. So normally that would be the element that you would name first, and also the element that you would list first in the formula. Okay, so if you look at the formula for most molecular compounds, like H2O, notice where hydrogen is in the periodic table versus oxygen. Hydrogen is way over to the left, so hydrogen goes first. Carbon dioxide, for carbon comes first, oxygen second. Notice carbon is to the left of oxygen, so the carbon comes first. And all of these nitrogen compounds. Nitrogen is to the left of oxygen in the periodic table, so nitrogen comes first. There are a couple exceptions here and there, but that's generally the way it goes. For one thing, any compound that contains carbon and hydrogen, usually you put the carbon first. But that's sort of a convention that comes out of organic chemistry, and organic chemistry is weird, so there are a lot of exceptions to the rules there. Okay, so the more metallic element comes first. Then you name the other element. As if it's a negative ion. In other words, you use the root of the name of the element ending in IDE. Like, say, carbon dioxide, oxide. And both elements should be preceded by a prefix giving the number of atoms of that element in the formula. Okay, so the form it takes is prefix followed by the name of the more metallic element, followed by prefix, again, another prefix for the second element, or sorry, followed by the root of the less metallic element, ending in IDE. Okay, so we can see some examples and it becomes much more obvious. First of all, the prefixes are actually the same as the prefixes used for hydrates. except you never encounter 1/2 in this list. So 1 would be a prefix of mono, 2 would be a prefix of di, 3 would be tri, 4 would be tetra, 5 would be penta, 6 would be hexa, 7 would be hepta, 8 would be octa, 9 would be nona, 10 is deca, 11, if you really want to go that far, and we do once in a while, would be undeca, and 12 is dodeca, and we're definitely not going to go any further than that. One exception to using the prefixes is that you never use the mono prefix for the first element in a name, even if there is only one of them. And that's because there's an enormous number of compounds that consist of one relatively metallic nonmetal surrounded by more metallic nonmetals like, say, oxygen. And since there's one atom in the center, that means that there would be an enormous number of compounds starting with the prefix mono. And things like alphabetical lists of chemicals or chemical dictionaries would have just a gigantic volume for M. It would be bigger than all of the other volumes combined. And so they figured that it was probably better just to name compounds like that based on the name of the element in the center rather than putting mono in front of it. But you do use di or tri or tetra if there's more than one, but never put mono at the very beginning of a name of a compound. And so some examples, you'll note that CO is carbon monoxide, not monocarbon monoxide. And you'll often, you'll notice another thing about this name is that it's carbon monoxide, not carbon monoxide. And that's because if the name of the second element, or if the name of the element begins with a vowel, you can usually drop the last vowel. Well, you can drop the last vowel if it's an O or an A. So if it's di or tri, you usually use the entire prefix. But if it's like mono or tetra or penta or any of the other prefixes, then you can normally drop the last vowel of the prefix in favor of the first vowel of the name. So, although you won't be wrong if you don't do that. Actually, I wouldn't count that as wrong, but I can't really speak for Sapling. I'm not sure if Sapling would count that as wrong or not. So it's best to be safe. If the name of the element starts with a prefix, drop the O or the A at the end of the, sorry, if the name of the element starts with a vowel, drop the O or the A at the end of the prefix. But if it's an I at the end of the prefix, keep it. Okay. So we have, CO2. Carbon dioxide. It's not monocarbon dioxide, it's carbon dioxide. We could have, say, SO2, sulfur dioxide. We could look at some of those nitrogen compounds that we had. NO, nitrogen monoxide. NO2 would be nitrogen dioxide. N2O would be dinitrogen monoxide. So once you get used to using these prefixes, it becomes really easy because the name of the compound just literally gives you the formula for the compound. Carbon monoxide means 1 carbon, 1 oxygen. And dinitrogen monoxide means 2 nitrogens, 1 oxygen. So once you know what the prefixes mean, you've got the formula too. Dinitrogen monoxide, better known as nitrous oxide. What else did we have? N2O3, dinitrogen trioxide. And N2O5, dinitrogen pentaoxide. There's also XeF6, one of the few compounds formed by any noble gas, would be xenon hexafluoride. There's P4O10, tetraphosphorus. Phosphor, nope, no U there. Tetraphosphorus decoxide. And so notice it's not decoxide, it's decoxide. And but you'll recall that these rules for naming these molecular compounds are very different from the rules for for ionic compounds. So you do need to be aware of what type of compound it is you're dealing with. Okay, that's enough for this segment. I'll be back in a moment with part B.